Alright, so chapter 1. And we have we can just stick with the ones that he recommended and see how that goes. So just 1.1, 1.2, 1.6. That's all we'll do right now. 1.1. What and how? A simple yet general definition provides sufficient response to the question, what is heat transfer? Heat transfer, or heat, is thermal energy in transit due to a spatial temperature difference. Whenever a temperature difference exists in a medium or between media, heat transfer must occur. As shown in figure 1.1, we refer to different types of heat transfer processes as modes. When a temperature gradient exists in a stationary medium, which may be solid or fluid, we use the term conduction to refer to the heat transfer that will occur across the medium. In contrast, the term convection refers to heat transfer that will occur between a surface and a moving fluid when they are at different temperatures. The third mode of heat transfer is termed thermal radiation. All surfaces of finite temperature emit energy in the form of electromagnetic waves. Hence, in the absence of an intervening medium, there is net heat transfer by radiation between two surfaces at different temperatures. And there are some pictures to go with it. 1.2. Okay, that was quick. Physical origins and rate equations. As engineers, it is important that we understand the physical mechanisms which underlie the heat transfer modes, that we be able to use the rate equations that quantify the amount of energy being transferred per unit time. 1.2.1 Conduction. At mention of the word conduction, we should immediately conjure up concepts of atomic and molecular activity, because processes at these levels sustain this mode of heat transfer. Conduction may be viewed as the transfer of energy from the more energetic to the less energetic particles of a substance due to interactions between the particles. The physical mechanism of conduction is most easily explained by considering a gas and using ideas familiar from your thermodynamics background. Consider a gas in which a temperature gradient exists, and assume that there is no bulk or macroscopic motion. That's a lot of commas. The gas may occupy the space between two surfaces that are maintained at different temperatures, as shown in figure 1.2. We associate the temperature at any point with the energy of gas molecules in proximity to the point. This energy is related to the random translational motion as well as to the internal rotational and vibrational motions of the molecules. Higher temperatures are associated with higher molecular energies. When neighboring molecules collide, as they are constantly doing, a transfer of energy from more energetic to the less energetic molecules must occur. In the presence of a temperature gradient, energy transfer by conduction must then occur in the direction of decreasing temperature. This would be true even in the absence of collisions, as is evident from figure 1.2. The hypothetical plane at x sub 0, x naught, is constantly being crossed by molecules from above and below due to their random motion. However, molecules from above are associated with a higher temperature than those from below, in which case there must be a net transfer of energy in the positive x direction. Collisions between molecules enhance this energy transfer. We may speak of the net transfer of energy by random molecular motion as a diffusion of energy. The situation is much the same in liquids, although molecules are more closely spaced and the molecular interactions are stronger and more frequent. Similarly, in a solid, conduction may be attributed to atomic activity in the form of lattice vibrations. The modern view is to ascribe the energy transfer to lattice waves induced by atomic motion. In an electrical non-conductor, the energy transfer is exclusively via these lattice waves. In a conductor, it is also due to the translational motion of the free electrons. We treat the important properties associated with conduction phenomena in Chapter 2 and in Appendix A. Examples of conduction heat transfer are legion. Whoa, many. The exposed end of a metal spoon suddenly immersed in a... here we go, the matrix. Alright, the exposed end of a metal spoon suddenly immersed in a cup of hot coffee is eventually warmed due to the conduction of energy through the spoon. On a winter day, there is significant energy loss from a heated room to outside air. This loss is principally due to conduction heat transfer through the wall that separates the room from air from the outside air. Heat transfer processes can be quantified in terms of appropriate rate equations. These equations may be used to compute the amount of energy being transferred per unit time. For heat conduction, the rate equation is known as Fourier's law. For the one-dimensional plane wall shown in figure 1.3, we have a temperature distribution T of x. The rate equation is expressed as, Q double prime sub x equals negative k times d capital T over dx. So the second derivative of q sub x is the constant times the derivative of t with respect to x. Alright, so the heat ux, q double prime x in watts per meter squared, is the heat transfer rate in the x direction per unit area perpendicular to the direction of transfer, and it is proportional to the temperature gradient dt dx in this direction. The parameter K is a transport property known as thermal conductivity, watts per meter dot Kelvin. And so again, thermal conductivity is watts per meter Kelvin, and is characteristic of the wall material. The minus sign is a consequence of the fact that heat is transferred in the direction of decreasing temperature. Under the steady state conditions shown in figure 1.3, the temperature distribution is linear, and the temperature gradient may be expressed as dt dx equals delta T over L. And the heat flux is then Q double prime sub x equals minus K times delta T over L. Or Q double prime sub x equals, okay, yes, it's saying the same thing. Okay, note that this equation provides a heat ux, that is the rate of heat transfer per unit area. The heat rate by conduction, Q sub x W, through a plane wall of area A is then the product of the flux Q sub x equals Q double prime sub x dot A. Example 1.1. We'll see if we're going to continue reading examples because it often doesn't play well in reading. But here we go. The wall of an industrial furnace is constructed from 0.15 meter thick fire clay brick having a thermal conductivity of 1.7 watts per meter dot Kelvin. Measurements made during steady state operation reveal temperatures of 1400 and 1150 kelvins. 1,400 and 1,150 kelvins at the inner and outer surfaces respectively. What is the rate of heat loss through a wall that is 0.5 meters by 1.2 meters on a side? Solution. First we start with the knowns. Steady state conditions with prescribed wall thickness, area, thermal conductivity, and surface temperatures. Okay. How that is a helpful known, I don't know. I don't know how they pick these things, but we must find wall heat loss. We draw a schematic, and there's a couple nice things. There's the wall with the dimensions, and it's showing the direction of the heat flow, showing call out to the area, and then there's a, is this also called a call out? A magnification call out, where they show the temperature on one side and the temperature on the other side, 1400 on the hot side, 1150 on the other side. So in the middle, the materials K, 1.7 watts per meter Kelvin, and then the length. So steady state conditions, these are our assumptions. Steady state conditions is the first one. The second one is one-dimensional conduction. Okay, that's what I thought. So the assumptions is what I always have trouble with. One-dimensional conduction through the wall, constant thermal conductivity. Now analysis, since heat transfer through the wall is by conduction, the heat flux may be determined from Fourier's law. Using equation 1.2, we have Q double prime sub x equals K delta T over L equals 1.7 watts per meter dot Kelvin times 250 K over 0.15. They get 2833 watts per meter squared for Q double prime of x. The heat flux represents the rate of heat transfer through a section of unit area and is uniform, that is to say, it's invariant, across the surface of the wall. The heat loss through the wall of the area A equals H times W is then Q sub x equals HW Q sub x double prime, and they get 1700 watts. And they have a comment saying to note the direction of heat flow and the distinction between heat flux and heat rate. Excuse me. That's not working. I'm trying to mute it so you don't have to. So you didn't have to hear me cough. Alright, so 1.2.2 Convection. The convection heat transfer mode is comprised of two mechanisms. In addition to energy transfer due to random molecular motion, that is diffusion, energy is also transferred by the bulk or macroscopic motion of the fluid. This fluid motion is associated with the fact that any instant large numbers of molecules are moving collectively or as aggregates. Such motion in the presence of a temperature gradient contributes to the heat transfer. Because the molecules in aggregate retain their random motion, the total heat transfer is then due to superposition of energy transport by the random motion of the molecules and by the bulk motion of the fluid. The term convection is customarily used when referring to this cumulative transport, and the term advection refers to transport due to bulk fluid motion. Again, convection is used when referring to cumulative transport. Advection refers to bulk fluid motion. We are especially interested in convection heat transfer, which occurs between a fluid in motion and a bounding surface when the two are at different temperatures. Consider fluid flow over the heated surface of figure 1.4. A consequence of the fluid surface interaction is the development of a region in the fluid through which the velocity varies from zero at the surface to a finite value, u sub infinity, associated with the flow. This region of the fluid is known as the hydrodynamic or velocity boundary layer. Moreover, if the surface and flow temperatures differ, there will be a region of the fluid through which the temperature varies from T sub s at y equals 0 to T sub infinity in the outer flow. This region, called the thermal boundary layer, may be smaller, larger, or the same size as that through which the velocity varies. In any case, if T sub s is greater than T infinity, convection heat transfer will occur from the surface to the outer flow. The convection heat transfer mode is sustained by both random molecular motion and the bulk motion of the fluid within the boundary layer. The contribution due to random molecular motion, that is, diffusion, dominates near the surface where the fluid velocity is low. In fact, at the interface between the surface and the fluid, y equals 0, so right at the beginning, the fluid velocity is 0, because of no slip condition, and heat is transferred by this mechanism only. The contribution due to bulk fluid motion originates from the fact that the boundary layer grows as the fluid progresses in the x direction. In effect, the heat that is conducted into this layer is swept downstream and is eventually transferred to the fluid outside the boundary. Appreciation of boundary layer phenomena is essential to understanding convection heat transfer. For this reason, the discipline of fluid mechanics will play a vital role in outer layer analysis of convection. Convection heat transfer may be classified according to the nature of the flow. We speak of forced convection when the flow is caused by external means, such as a fan, a pump, or atmospheric winds. As an example, consider the use of a fan to provide forced convection air cooling of hot electrical components on a stack of printed circuit boards, figure 1.5a. In contrast, for free, that is, or to say natural convection, the flow is induced by buoyancy forces which are due to density differences caused by temperature variations in the fluid. An example is the free convection heat transfer that occurs from hot components on vertical array circuit boards in the air. Air that makes contact with the components experiences an increase in temperature and hence a reduction in density. Since it is now lighter than the surrounding air, buoyancy forces induce a vertical motion for which warm air ascending from the boards is replaced by an inflow cooler ambient air. Did I go past? Nope, we're still at 1.2. While we have presumed pure forced convection in figure 1.5a, the pure natural convection of 1.5b conditions correspond. Sorry, that's my alarm. Just turn that off. Eventually. There we go. Alright, where was I? I have no idea. 1.5. Corresponding mixed combined forces, natural convection may exist. For example, if velocities associated with the flow of 1.5a are small and or buoyancy forces are large, a secondary flow that is comparable to the imposed forced flow could be induced. In this case, the buoyancy-induced flow would be normal to the forced flow and could have a significant effect on convection heat transfer from the components. In Figure 1.5b, mixed convection would result if a fan were used to force air upward between the circuit boards, thereby assisting the buoyancy flow, or downward, thereby opposing the buoyancy flow. We have described the convection heat transfer mode as energy transfer occurring within a fluid due to combined effects of conduction and bulk fluid motion. Typically, the energy that is being transferred is the sensible or internal thermal energy of a fluid. However, for some convection processes, there is, in addition, latent heat exchange. This latent heat exchange is generally associated with a phase change between the liquid and vapor states of the fluid. Two special cases of interest in this text are boiling and condensation. For example, convection heat transfer results from fluid motion induced by vapor bubbles generated at the bottom of a pan of boiling water, or by the condensation of water vapor on the outer surface of a cold water pipe. They have some figures here. One is a fan blowing over the elements, and another one showing the air blowing over the elements, a boiling pot of water. Okay. They give in Table 1.1 typical values of convection heat transfer coefficient and for different processes, and starting with the smallest and going to the biggest values of H. The smallest would be free convection, and then forced convection, and then convection with phase change, which is huge numbers. Free convection 2 to 25 for gases, 50 to 1,000 for liquids. For forced convection, it was 25 to 250 for gases, and 100 to 20,000 for liquids. Wow, okay, these are big jumps. And then convection with phase change goes for boiling or condensing, 2,500 to 100,000. So, regardless of the nature of convection heat transfer process, the appropriate rate equation is of the form Q double prime equals H times T sub S minus T infinity, where Q double prime is the convective heat UX in watts per meter squared, is proportional to the difference between the surface and fluid temperatures T sub S and T sub infinity. Respectively, this expression is known as Newton's law of cooling, and the parameter H in watts per meter squared Kelvin is termed the convection heat transfer coefficient. This coefficient depends on conditions in the boundary layer, which are influenced by surface geometry, the nature of the fluid motion, and an assortment of fluid thermodynamic and transport properties. Any study of convection ultimately reduces to a study of the means by which H may be determined. Although consideration of these means is deferred to Chapter 6, convection heat transfer will frequently appear as a boundary condition in the solution of conduction problems, Chapter 2 through 5. In the solution of such problems, we presume H to be known using typical values in Table 1.1. When equation 1.3a is used, the convection heat flux is presumed to be positive if heat is transferred from surface T sub S, from surface, and negative if heat is transferred to the surface. Alright, so I'll read that again with proper inflection. When equation 1.3a is used, the convection heat flux is presumed to be positive if heat is transferred from the surface, and negative if heat is transferred to the surface. Positive if heat is transferred from the surface. So it's good to lose your heat. It's positive to lose your heat if you are the surface, and it's negative to gain it. However, nothing precludes us from expressing Newton's law of cooling as Q double prime equals H times T infinity minus T sub S, which is just the negative of the one above, in which case heat transfer is positive to its... okay, let's just stick with one. Alright, but you should be able to see it's positive if this is greater than that, so the T away minus the T of the surface, if the T away is greater, then it will be transferred from away to the surface, and that's how we know it's positive. 1.2.3. He didn't say to do radiation, but let's just scroll through some equations here. Those aren't very pretty. An example, a pipe, emissive power, radiation. 1.2.4, thermal resistance concept. Interesting. And keep going all the way to, what did he say? 1.6, right? Yeah, 1.6. Alright, well hopefully we're not using any of these equations for now. Or maybe this one I know we'll use. Q equals mc delta T. I guess we're supposed to just remember that. Maybe I'll come back and do a separate reading for the stuff we're skipping right now. And a conducting rod of diameter D and electrical resistance. Continuing. Example 1.5. This is all still just from 1.3. Okay. There's a lot of examples. Alright, let's do this a different way. Okay, a lot of equations still. Sorry, bear with me. Units and dimensions, length, mass, time, temperature. Definitely not reading this part. Exa, yeah, I thought that's what that E was. We saw an E earlier. And mu. Alright, anyways. 1.6. I remember seeing 1.5. 5. Analysis of heat transfer problems methodology. Alright, I'm going to read that. Okay. A major objective of this text is to prepare you to solve engineering problems that involve heat transfer processes. To this end, numerous problems are provided at the end of each chapter. In working these problems, you will gain a deeper appreciation for the fundamentals of the subject, and you will gain confidence in your ability to apply these fundamentals to the solution of engineering problems. In solving problems, we advocate the use of a systematic procedure characterized by a prescribed format. We consistently employ this procedure in our examples, and we require our students use it in their problem solutions. It consists of the following steps: known, find, schematic, assumptions, properties, analysis, comments. Yeah, I guess I was hoping for more than that. After carefully reading the problem, state briefly and concisely what is known about the problem. Do not repeat the problem statement. Find. State briefly and concisely what must be found. Draw a schematic of the physical system. This is schematic. If application of the conservation laws is anticipated, represent the required control surface or surfaces by dashed lines on the schematic. Identify relevant heat transfer processes by appropriately labeled arrows on the schematic. List all pertinent simplifying assumptions. That's assumptions. 5. Properties. Compile property values needed for subsequent calculations and identify the source from which they are obtained. 6. Analysis. Begin your analysis by applying appropriate conservation laws and introduce rate equations as needed. Develop the analysis as completely as possible before substituting numerical values. Perform the calculations needed to obtain the desired results. 7. Comments. Discuss your results. Such a discussion may include a summary of key conclusions, a critique of the original assumptions, and an inference of trends obtained by performing additional what-if parameter sensitivity calculations. What does that mean? Obtained by performing additional what-if and... Okay, gotcha. The importance of the following steps 1 through 4 should not be underestimated. They provide a useful guide to thinking about a problem before effecting its solution. In step 7, we hope you will take the initiative to gain additional insights by performing calculations that may be computer-based. The software accompanying this text is a suitable tool for effecting such calculations. And then they have an example. some assumptions, so that should be good. I'll review that one. Still have difficulty with some of those things. I just want to solve the problem and just be done with it, or so I'll give that some practice. 1.6 Relevance of heat transfer. We will devote much time to acquiring an understanding of heat transfer effects and to developing the skills needed to predict heat transfer rates and temperatures. Let me move this microphone. Alright, I'm going to start over. We will devote much time to acquiring an understanding of heat transfer effects and to developing the skills needed to predict heat transfer rates and temperatures that evolve in certain situations. What is the value of this knowledge? To what problems may it be applied? A few examples will serve to illustrate the rich breadths of applications in which heat transfer plays a critical role. The challenge of providing sufficient amounts of energy for humankind is well known. Adequate supplies of energy are needed not only to fuel industrial productivity, but also to supply safe drinking water and food for much of the world's population, and to provide the sanitation necessary to control life-threatening diseases. To appreciate the role heat transfer plays in the energy challenge, consider a flow chart that represents the energy use in the United States, as shown in Figure 1.11a. Currently, about 58% of the nearly 110 exajoules of energy that's what I read before, that's where I saw the exa, of energy that is consumed annually in the United States is wasted in the form of heat. Nearly 70% of the energy used to generate electricity is lost in the form of heat. The transportation sector, which relies almost exclusively on petroleum-based fuels, utilizes only 21.5% of the energy it consumes. The remaining 78.5% is released in the form of heat. Although the industrial and residential commercial use of energy is relatively more efficient, opportunities for energy conservation abound. Creative thermal engineering, utilizing the tools of thermodynamics and heat transfer, can lead to new ways to 1. Increase the efficiency by which energy is generated and converted, 2. Reduce energy losses, and 3. Harvest a large portion of the waste heat. As evident in Figure 1.11a, fossil fuels, petroleum, natural gas, and coal, dominate the energy portfolio in many countries, such as the United States. The combustion of fossil fuels produces massive amounts of carbon dioxide. The amount of CO2 released in the United States on an annual basis due to combustion is currently 5.99 exagrams, and that's 5.99 times 10 to the 15 kilograms. That's a lot. As more CO2 is pumped into the atmosphere, mechanisms of radiation heat transfer within the atmosphere are modified, resulting in potential changes in global temperatures. In a country like the United States, electricity generation and transportation are responsible for nearly 75% of the total CO2 released into the atmosphere due to energy use. What are some of the ways engineers are applying the principles of heat transfer to address issues of energy and environmental sustainability? The efficiency of a gas turbine engine can be significantly increased by increasing its operating temperature. Today, the temperatures of combustion gases inside these engines far exceed the melting point of the exotic alloys used to manufacture the turbine blades and vanes. Safe operation is typically achieved by 3 means. First, relatively cool gases are injected through small holes at the leading edge of the turbine blade. These gases hug the blades as they are carried downstream and help insulate the blade from the hot combustion gases. Second, thin layers of very low thermal conductivity ceramic thermal barrier coating are applied to the blades and vanes to provide an extra layer of insulation. These coatings are produced by spraying molten ceramic powders onto engine components using extremely high temperatures sources such as plasma spray guns. Good lord. That can operate in excess of 10,000 kelvins. I thought we said high temperatures were a problem for these pieces. Third, the blades and vanes are designed with intricate internal cooling passages, all carefully configured by the heat transfer engineer to allow the gas turbine engine to operate under extreme conditions. alternative sources constitute a small fraction of the energy portfolio of many nations, as illustrated in the flowchart of Figure 111A for the United States. The intermittent nature of the power generated by sources such as wind and solar irradiation limits their widespread utilization, and creative ways to store excess energy for use during low power generation periods are urgently needed. Emerging energy conservation devices such as fuel cells could be used to 1. Combine excess electricity that is generated during the day in a solar power station, for example, with liquid water to produce hydrogen, and 2. Subsequently convert the stored hydrogen at night by recombining it with oxygen to produce electricity and water. Roadblocks hindering the widespread use of hydrogen fuel cells are their size, weight, and limited durability. As with the gas turbine engine, the efficiency of a fuel cell increases with the temperature, but high operating temperatures and large temperature gradients can cause the delicate polymeric materials within a hydrogen fuel cell to fail. More challenging is the fact that water exists inside any hydrogen fuel cell. If this water should freeze, the polymeric materials within the fuel cell would be destroyed, and the fuel cell would cease operation. Because of the necessity to utilize very pure water in a hydrogen fuel cell, common remedies such as antifreeze cannot be used. What heat transfer mechanisms must be controlled to avoid freezing of pure water within a cell located at a wind farm or solar energy station in a cold climate? How might your developing knowledge of internal forced convection, evaporation, or condensation be applied to control the operating temperatures and enhance the durability of a fuel cell, in turn promoting more widespread use of solar and wind power? Due to the information technology revolution of the last 2 decades or more, 2 decades, strong industrial productivity growth has brought an improved quality of life worldwide. Many information technology breakthroughs have been enabled by advances in heat transfer engineering that have ensured precise control of temperature systems ranging in size from nanoscale integrated circuits to microscale storage media, including compact disks, to larger data centers filled with heat-generating equipment. As electronic devices become faster and incorporate greater functionality, they generate more thermal energy. Simultaneously, the devices have become smaller. Inevitably, heat fluxes in watts per meter squared and the volumetric energy generation rates, watts per meter cubed, keep increasing, but the operating temperatures of the devices must be held to reasonably low values to ensure their reliability. For personal computers, cooling fans, also known as heat sinks, are fabricated of a high thermal conductivity material, usually aluminum, and attached to the microprocessors to reduce their operating temperatures. As shown in Figure 1.13, small fans are used to induce forced convection over the fins. The cumulative energy that is consumed worldwide just to 1. Power the small fans that provide the airflow over the fins, and 2. Manufacture the heat sinks for personal computers is estimated to be over 10 to the 9th kilowatts times hours per year. How might your knowledge of conduction, convection, and radiation be used to, for example, eliminate the fan and minimize the size of the heat sink? Further improvements in microprocessor technology are currently limited by our ability to cool these tiny devices. Policymakers have voiced concern about our ability to continually reduce the cost of computing and, in turn, as a society, continue the growth in productivity that has marked the last 30 years, specifically citing the need to enhance heat transfer in electronics cooling. How might your knowledge of heat transfer help ensure the continued industrial productivity into the future? Heat transfer is important not only in engineered systems but also in nature. Temperature regulates and triggers biological responses in all living systems and ultimately marks the boundary between sickness and health. 2 common examples include hypothermia, which results from excessive cooling of the human body, and heat stroke, which is triggered in warm, humid environments. Both are deadly. Both are associated with core temperatures of the body exceeding physiological limits. Both are directly linked to the convection, radiation, and evaporation processes occurring at the surface of the body, the transport of heat within the body, and the metabolic energy generated volumetrically within the body. Recent advances in biomedical engineering, such as laser surgery, which have been enabled by successfully applying fundamental heat transfer principles. While increased temperature results from contact with hot objects may cause thermal burns, beneficial hyperthermal treatments are used to purposely destroy, for example, cancerous lesions. In a similar manner, very low temperatures might induce frostbite, but purposeful localized freezing can selectively destroy diseased tissue during cryosurgery. Many medical therapies and devices therefore operate by destructively heating or cooling diseased tissue while leaving the surrounding healthy tissue unaffected. The ability to design many medical devices, I got some water, and to develop the appropriate protocol for their use hinges on the engineer's ability to predict and control the distribution of temperatures during thermal treatment and the distribution of chemical species in chemotherapies. The treatment of mammalian tissue is made complicated by its morphology. As shown in Figure 114, the flow of blood within the venular and capillary structure of the thermally treated area affects the heat transfer through advection processes. Larger veins and arteries, which commonly exist in pairs throughout the body, carry blood at different temperatures and advect thermal energies at different rates. Therefore, the veins and arteries exist in a counterflow heat exchange arrangement, with warm arteriolar blood exchanging thermal energy with the cooler venular blood through the intervening solid tissue. Networks of smaller capillaries can also affect local temperatures by perfusing blood through the treated area. Perfusing. Don't know what that means. In subsequent chapters, example and homework problems will deal with the analysis of these and many other thermal systems. Summary. Although much of the material of this chapter will be discussed in greater detail, you should now have a reasonable overview of heat transfer. You should be aware of the several modes of transfer and their physical origins. You will be devoting much time to acquiring the tools needed to calculate heat transfer phenomena. However, before you can use these tools effectively, you must have the intuition to determine what is happening physically. Specifically, given a physical situation, you must be able to identify the relevant transport phenomena. The importance of developing this facility must not be underestimated. The example and problems at the end of this chapter will launch you on the road to developing this intuition. You should also appreciate the significance of the rate equations and feel comfortable in using them to compute transport rates. These equations, summarized in Table 1.5, should be committed to should be committed to memory. You must also recognize the importance of conservation laws and the need to carefully identify control volumes. With the rate equations, the conservation laws may be used to solve numerous heat transfer problems. Lastly, you should have begun... what should I have begun? You should have begun to acquire an appreciation, for the terminology and physical concepts that underpin the subject of heat transfer. Test your understanding of the important terms and concepts introduced in this chapter by addressing the following questions. What are the physical mechanisms associated with heat transfer by conduction, convection, and radiation? What is the driving potential for heat transfer? What are analogies to this potential and to heat transfer itself for the transport of electric charge? What is the difference between heat UX and heat rate? What are their units? What is a temperature gradient? What are its units? What is the relationship of heat flow to a temperature gradient? What is the thermal conductivity? What are its units? What role does it play in heat transfer? What is Fourier's law? Can you write the equation from memory? Q double prime equals H delta T over L? Maybe? I don't know. Something like that. I don't know. I think there was... whatever. If heat transfer by conduction through a medium occurs under steady-state conditions, will the temperature at a particular instant vary with location in the medium? Will the temperature at a particular location vary with time? What is the difference? Wow, there's a lot of questions. Okay, let's just go through it. Keep going. Almost done. What is the difference between natural convection and forced convection? What conditions are necessary for the development of a hydrodynamic boundary layer? A thermal boundary layer? What varies across a hydrodynamic boundary layer? across a thermal boundary layer. If convection heat transfer for a flow of a liquid or vapor is not characterized by liquid, vapor, and phase change, what is the nature of energy being transferred? What is it if there is such a phase change? Yeah, there was big differences there. What is Newton's law of cooling? Can you write the equation from memory? What role is played by the convection heat transfer coefficient in Newton's law of cooling? What are its units? What effect does convection heat transfer from or to the surface of a solid bounded by the surface? What is predicted by the Stefan-Boltzmann law, and what unit of temperature must be used with the law? Can you write the equation from memory? What is the emissivity, and what role does it play in characterizing radiation transfer at a surface? What is irradiation? What are its units? What two outcomes characterize the response of an opaque surface to incident radiation? What outcome affects the thermal energy of the medium bounded by the surface, and how? What property characterizes this outcome? What conditions are associated with the use of the radiation heat transfer coefficient? Can you write the equation used to express net radiation exchange between a small isothermal surface and a large isothermal enclosure? Consider the surface of a solid that is at an elevated temperature and exposed to cooler surroundings. By what mode or modes is the heat transferred from the surface if 1. It is intimate, that is to say, perfect contact with another solid. 2. It is exposed to the flow of a liquid. 3. It is exposed to the flow of a gas. And 4. It is in an evacuated chamber. What is the inherent difference between the application of conservation of energy over a time interval and at an instant of time? And lastly, what is thermal energy storage? How does it differ from thermal energy generation? What role do the terms play in a surface energy balance? And then there's an example after the review. And the references, and then the problems. Next video, thank you for listening. Good luck in the class. Next video will be on chapter 2.1 to 2.3. So 2.1, 2.2, and 2.3.